Okay, so today we're going to start talking about carbon storage, and this is where it gets a little more engineering-y because we have calculations and planning and stuff that we have to do. But this is one of my favorite units in the course. I hope that you guys enjoy it too. So, carbon storage, let's see. I need to update this, but as of April 2022, we had almost 419 parts per million of CO2 in the atmosphere. I think it's closer to 420, 422 right now, but anyways, it's around there. And so you can convert that to kilograms of carbon dioxide, and it turns out it's roughly 3.3 quadrillion kilograms. So that's kind of a large number because the atmosphere is very large. The IEA, which is the International Energy Agency, estimated that in all of 2021, the energy-related CO2 emissions, so this is from burning fossil fuels and also producing them and transporting them, together, those made up about 36 billion kilograms. And so between these two, what if you wanted to store all this somewhere? So imagine you can get it out of the atmosphere and then you have to put it somewhere. So what are the options? Okay, so at normal temperature and pressure, CO2 density is about 1.8 kilograms per cubic meter. And so you can do a calculation. If you took all the CO2 in the atmosphere, it would be about 1.8 quadrillion cubic meters. Similarly, the 2021 energy-related emissions would be about 20 billion cubic meters. Okay, so just to think about how big that is. Texas has a surface area of about 700 billion square meters. And so if you took all of the CO2 in the atmosphere and spread it over Texas, I'm not recommending you do this, but if you were to do that, it would cover the size of Texas and it would be about 2.5 kilometers thick. So that's, a fair amount of CO2. Just the 2021 energy-related emissions, it would be about 2.8 centimeters thick. And again, we're neglecting the compressibility of the CO2 here, but that's roughly how much it is. So the point here is that if you're doing carbon removal, you need somewhere to put all that CO2. You can't just store it in a tank. There's way too much of it, okay? And so the question is, where else could we put the CO2? And so the most promising option, and probably the one that's gotten the most research attention, has been what they call geological storage. And this is essentially pumping it underground, either into depleted oil and gas fields or into saline aquifers, basically that are deep enough that you don't have to worry about the CO2 leaking back to the surface, because obviously we want to prevent that. We believe that the sedimentary basins around the world have somewhere between 8 and 55 trillion kilograms of CO2 storage capacity. So if we go back here, that's, we're not going to remove all the CO2 from the atmosphere, and that's probably a silly goal anyway. We wouldn't want to do that. But it offers, many years of carbon emissions if we're just abating the energy-related carbon emissions. So if you just look at the orders of magnitude, in 2021, it was about 3.6 times 10 to the 10. And we've got, somewhere around, 100 to 1,000 times that in available storage. So if you do some combination of reducing the carbon intensity of energy production to begin with, and then some type of abatement of the unavoidable carbon emissions, you've got, potentially hundreds of years worth of storage in the subsurface. Now, when you run out of that storage, I guess you'll have to figure out something else. But this may be a potential solution here. Another potential place to store the carbon is in the ocean. And actually, the oceanic carbon sink could potentially have a lot more than what we have in the subsurface. So again, looking at orders of magnitude here, geological storage, we are in the order of trillions of kilograms. Oceanic storage, we're on the order of about 1,000 times that, quadrillions. The IPCC did some calculations on this a while back. And there's a number of different ways that you could store CO2 in the ocean. You could inject it as a gas or as liquid CO2 and just have it dissolve, or store it as liquefied CO2 on the bottom of the ocean, which would actually be dense and so it would stay there. You could even store it as a hydrate. And so there's a number of different ways of doing this. Now, there's a little bit of a problem with oceanic storage of CO2. You'll remember back in our discussion of the carbon cycle, what does CO2 do to water? Right? It makes it more acidic because it reacts with the water molecules and forms carbonic acid. And so if you're going to store a bunch of CO2 in the ocean, you have to have some way of counteracting that acidification behavior. And so there's a technique that's getting a lot of attention right now. There's several startup companies that I'm aware of who are working on this. It's called ocean alkalinity enhancement. And essentially, the way this works is that you add something to the seawater that buffers the pH, okay? There's a number of different chemicals that are being looked at right now. But it's it could be it could be lime, it could be different types of silicate minerals, but these are things that would raise the pH again after you dissolve the CO2. You could even think of things that are extracted from seawater in the process of desalination. So possibly using waste products here for the alkalinity enhancement. But the way it works in terms of the chemistry is that you're going to add alkaline materials. So these could be hydroxides. There are other chemicals that have been looked at also that can react with CO2. And what they do is they precipitate bicarbonate minerals out of solution. And those just fall to the bottom of the ocean, where then they are sequestered as mineral phases, which again is the best way of the most secure way of sequestering CO2. So this is potentially a solution. Now, obviously, you're going to have to come up with ways of spreading these materials in the ocean. They're looking at what the effects on wildlife and marine ecosystems are. So there's still a lot of work to be done, but this is potentially how you can utilize that very large potential carbon sink in the ocean. Right, so kind of got ahead of myself here. So short-term and long-term impacts on the ocean ecosystems, how much of these materials you actually need. If it's in the gigatons range, you're going to need to think about how you produce them and how you supply them. And then getting public buy-in about dumping a bunch of stuff in the ocean, that's always a little bit of a tricky matter. And so you have to think carefully about, your ability to do this. There's this concept called social license to operate. And any type of activity, it's usually applied to, industrial type activities, but any activity that you do, you have to have public buy-in, or else they're going to, you're going to get opposition to that and potentially be, barred legally from doing it. So you have to think carefully about how you're going to get people, invested in, making this happen. It's interesting to talk about. We'll talk about this later in the semester, but I think that, it's tempting to think that anything that helps decarbonize energy supplies and reduces CO2 content in the atmosphere, everybody's going to be in favor of that because that's a net positive thing. But there's a lot of areas where you do see resistance to certain things. And so it's always important to keep that in mind, that it's just not automatic acceptance of these things. Okay, so that's oceanic carbon storage. It's about all we need to talk about. But let's talk about geological carbon storage. So what we're looking at here, this is a piece of rock, and it's a type of rock called basalt. And basalt has various minerals in it that can react with carbon dioxide and form minerals. So this is a particular type of basalt called a vesicular basalt, and it's got these holes in it. Those are vesicles, and they're formed by air pockets that are there while the rock is solidifying. And what we're looking at here is this is a chunk of calcium carbonate mineral that has filled one of these vesicles by the reaction of this rock with carbon dioxide. And this is the ultimate goal of geological carbon storage. You basically want to pump the CO2 down into the subsurface, either as a gas, a liquid, or a supercritical fluid, and then hold it there long enough for it to react with the minerals that are present down there and form these solid mineral phases. Because once you form these solid mineral phases, they can't leak, they can't move around. It's a very secure form of storage. And that's ultimately what the goal is here. Okay, so let's think about the actual engineering principles of doing CO2 injection. So this is the phase diagram for carbon dioxide. And it's obviously separated into these different regions depending on the pressure and temperature that you're at. The critical point is here. It's at about 305 Kelvin, I think, and around 1100 psi. So once you get above that, you're dealing with a supercritical fluid. And I think I mentioned this the other day in class, but a supercritical fluid is really just a dense gas. It has gas-like viscosity with liquid-like density. And so it's easy to pump, but you get a lot of it, a lot of mass per unit volume. There's the liquid region, the gas region, and then there's the hydrate region over here. And I've spent a lot of my career looking at not necessarily CO2 hydrates, but methane hydrates. And so I, live my life kind of in this region, but there's a lot of other region in here as well. Okay, so rocks are full of holes. This often surprises people, but they are full of holes, and usually those holes contain salty water. We call those holes pores, and we say that rocks are porous. They are porous materials. And like I said, it's usually salty water. Sometimes it's oil and gas that can be extracted, but not usually. Now, because the rocks are full of holes and those holes are full of salty water, the salty water is going to have a particular pressure associated with it. And that's because if you're at a particular depth, you've got all those rocks and all that salty water above you, and gravity makes it push down on you. And so there's a pressure being exerted on you. And we call that the hydrostatic pressure. And we can calculate what that pressure is at a particular depth by integrating the density as a function of depth down to that, and then multiplying that by gravity. If you assume that the density is constant, that your fluid is incompressible, then this gets easy. It's just rho times g times the depth, but this is the general term. So you can calculate what that depth is at any point within the Earth. Okay, so like I said, if it's incompressible, we have pressure as a function of depth. It's just density times gravity times depth. And for salt water, it turns out that the pressure increases at roughly 10 kilopascals per meter, or about 0.447 psi per foot. So we call that a hydrostatic pressure gradient. And so what you can do now is that we can convert this pressure axis here to a depth axis to get an idea of what state the CO2 is going to be at, depending on what depth and what temperature we're at. Okay, so if I just take this pressure and I map it onto an equivalent depth axis, assuming that the pressure is hydrostatic, so it's only due to the weight of the water column. This is what it looks like. And so you can see that below, roughly 2,500 feet, generally you are going to be in the supercritical state. And so most of the time when we're doing CO2 injection, it ends up being a supercritical fluid in the subsurface. And that's a good thing because, again, a given mass of CO2 will take up a lot less space at depth because it's a lot denser than it is in the gas phase. Okay, now the other thing we can do here is we can think about mapping the temperature axis onto depth as well. If we think about how the temperature varies within the Earth. I'll explain more about this when we do our unit on geothermal, but basically, as you go deeper, the Earth gets hotter, and it's a combination of mantle convection bringing the heat from the core up to the base of the crust. So the base of the crust is hot, and then the surface is not hot. So you've got a temperature gradient across the crust. And there's also a minor contribution from the decay of radioactive minerals in the crust. And so the rate at which the temperature increases with depth, it varies, and it varies considerably depending on local characteristics of the rocks and crustal thickness, fluid circulation, that sort of thing. But a good benchmark is that it's approximately 0.01 degrees Fahrenheit per foot, so 1 degree per 100 feet. See, this is like the one situation in which imperial units work out easier. 1 degree per 100 feet, which is equivalent to 18 degrees Celsius per kilometer, which is a little bit less of an easy thing to remember. And so, if we assume some typical average temperature in the subsurface or at the surface, which, 60 degrees Fahrenheit is often what we assume for that. That's not to say that the average air temperature is 60 degrees Fahrenheit, but if you dig down like 6 feet or so, it's a pretty stable temperature right there. That's, how a lot of geothermal systems work. But anyway, we can use that to map a pressure temperature line onto our diagram. Okay, and so this is a very typical temperature versus depth profile. So again, this is 1 degree Fahrenheit per 100 feet, and assuming that pore pressure is hydrostatic. So we've converted this to a typical path that you would take. And so if you're injecting carbon dioxide, you would start somewhere down here, 1 atmosphere and, about 289 Kelvin. And as the CO2 goes down the well that you're injecting it into, it'll follow roughly this trajectory, and it will cross from the gaseous region into the supercritical region. Okay. And so again, for depths greater than 2,400 feet, we cross into the supercritical region, and we get that densification that we expect to see. Okay. Okay, and so just by way of comparison, the density of supercritical carbon dioxide is around a little more than 700 kilograms per cubic meter. And so what that means is if we go from standard temperature and pressure, if we took 100 cubic meters of carbon dioxide, if we get down to 2.5 kilometers depth, so that's about 8,200 feet, that 100 meters would be compressed down to a volume of 0.27 cubic meters. So it takes up a lot less volume. And this is one of the reasons why we can store so much in the subsurface, because it gets really compressed. Okay, now here's an interesting thing to think about. So this is for carbon storage underneath the land. Okay, so we're doing land-based operations here. What if we went offshore? Because there's a tremendous amount of potential sedimentary basin storage offshore. And in fact, I think ExxonMobil is looking at this off the Texas Gulf Coast, looking at offshore CO2 storage. So what about doing that? So the temperature profile offshore is a lot different than it is onshore. So if you're operating in deep water, the seafloor temperature is generally around 3 degrees Celsius. It's very cold down there. And so let's imagine that we're operating in 2,000 feet of water, and we're at around 3 degrees Celsius at the seafloor. So the temperature trajectory would look something like this. So we've got 2,000 feet of seawater on top of us. So the pressure already starts there. And then the pressure and temperature increase along this line here. So actually, in a lot of cases at the seafloor, the CO2 can be, or close to the seafloor, the CO2 can be stored as a hydrate phase. Now, hydrates are interesting. They're ice-like substances where you've got a kind of a cage of water molecules arranged around what's called a guest molecule. And they're quite a bit denser than supercritical CO2. But the actual amount of CO2 per unit volume is not as great because you've got a lot of water molecules in there. But if you inject it deep enough, you can actually get to liquid CO2 region. Question?
Given certain like like a leak or like big swell would be a bigger deal for like a leak.
Yeah, so that's a good question. So if you had leakage into the water column, would the acidification be more problematic than leakage into the atmosphere? And I don't really have a good answer for that. You know, which is worse, the CO2 going back into the atmosphere where you've got, you know, global warming potential versus leaking into the water where it has acidification potential. I don't know. Neither one is good, and I think you want to try to avoid it. That's probably my best answer for that. But yeah, it's something to think about. Okay. Great. So another thing you can do is you can compare what the densities would be. So let's imagine we've got liquid CO2 here. We're operating offshore. So we can compare the densities of liquid CO2 and supercritical CO2 to see where you get more bang for your buck, so to speak, in terms of carbon storage. So this is a little bit of a different phase diagram here. I've got temperature on the x-axis, and this is density on the y-axis here. And then what we've got on these ISO lines, these are isobars. So these are lines of constant pressure. So let's take an arbitrary example. So we're storing at a depth of 3,500 feet. So for onshore, that's going to be 3,500 feet below ground level. For offshore, that's going to be 3,500 feet below sea level. So we've got 2,000 feet of water and then an additional 1,500 feet below the seafloor. So the pressure in both cases is going to be about 10.8 megapascals because we're assuming the pressure is hydrostatic. It doesn't matter. But the big difference is that in the onshore example, it's going to be a lot warmer at that depth than it will be offshore, because remember, offshore, we start at a lower temperature at the seafloor. And that means that because we're operating in the liquid CO2 region, this is where we are offshore compared to onshore. And you can actually store more CO2 in the liquid phase offshore than you can onshore in the supercritical phase. So, you know, there could be some real significant upside to storing CO2 offshore. The problem with that is that it's a lot more difficult to get CO2 offshore. You know, as expensive as it is to build pipeline infrastructure on land, it's even more expensive to do it offshore. And then you have to think about taking it out there by, you know, tanker ship or something. So there's possibly a lot of drawbacks to that. But it is something to think about. And that could be a potential engineering solution there somehow, if you can come up with it. Okay, so that's a little digression into offshore versus onshore, supercritical versus liquid CO2. I think the upshot there is liquid CO2 is denser. If you can get it to that state, then that's good, but otherwise supercritical is the way to go. Okay, so where exactly can you store the CO2 in the subsurface. So there's a number of different places that you can do it. So you could store it just in a saline aquifer. So like I said, most rocks are full of holes, and those holes contain salty water. So there's a lot of salty water potential storage, pore volume in the subsurface. But you can also inject it into an oil or a gas reservoir, either to produce more oil or gas, or simply to sequester it down there. And excuse me, injection into depleted oil and gas reservoirs actually has a lot of advantages. So you see this thing here called impermeable cap rock. We'll talk about what that is in a little bit, but that's basically a rock where the pores are so small that they don't permit the passage of the CO2 through them. And that's always something you have to worry about when you're injecting the CO2 into a saline aquifer is, how good is the cap rock? Now, if you've got a depleted oil field or depleted gas field, you know that the seal is good because they held the oil and the gas. It held the oil and the gas down. So there's less of a risk for the seal if you're looking at a depleted oil and gas reservoir. But they're few and far between, right? Most of the storage is going to be in saline aquifers. So it's just something to think about. You can also inject the CO2 into a coal seam. Coal is a pretty good storage volume. There's a lot less of it than there is saline aquifers, but this is also something you could look at. And so again, you can try to use the CO2 to produce natural gas or to produce oil from the subsurface, or not, or you can just inject it down there and let it sit there. But basically, you've got to find this pore volume. So this is what the types of pores actually look like. So if you're looking at a saline aquifer, that's generally going to be a sandstone type rock. And so this is a rock where the grains are made up mainly of quartz. If you look at a microstructural image, it looks something like this. So this is a Berea sandstone, which is a very common rock for doing experimental work because it's got these very nice, almost uniformly sized grains and good, open pore space as well. So that's a 100 micron scale bar. So the pores are on the order of 100 to 200 microns. So that's big as far as pores go in sandstones. I know it doesn't sound like a whole bunch. It's interesting to think about. Do you know what the diameter of your hair is? Anybody know? It's about 100 microns. Yeah. So yeah, the pores in a typical coarse grained sandstone are about the size of your hair. So they're pretty small, but not like ultra microscopic. You're probably wondering, actually, this is just a little side note, why are the pores blue? Well, this is a thin section image. And what they've done here, a lot of the time when we make thin sections, you take your core sample and you inject a blue epoxy into it. Then the epoxy hardens, and then you can cut the rock and cut it to a very thin wafer that will transmit light through the epoxy. And then you can look at it under a microscope, and the blue spots show you where the pore volume is, and then everything else is going to be solid. So that's just a typical way of doing that. Okay, so that's for sandstone. Now, another potential sequestration target is basalt. And I mentioned this, we saw an example of this earlier. The reason that basalt is so good for CO2 injection is that it reacts very quickly with the CO2 to create minerals. And so it's a very, very good way of doing that. And they're doing this in Iceland, actually. There's a company that called Carbfix, which is injecting carbon dioxide into the basalt. They have a lot of basalt in Iceland because it's right on the Mid-Atlantic Ridge. And so they're doing a pretty good job there. But again, this is some more of this vesicular basalt. You can see how big the pores are in this compared to what we have in the Berea sandstone. So it's a lot easier to inject CO2 into the basalt because the pores are so much larger. But basically, you have to think about, what's the fraction of the rock is actually made up of the pores. And we've defined that as the porosity, which is simply the volume of the voids divided by the total volume of the rock. So this basalt has about 10% porosity. Brea sandstone is about 20% porosity. So there's more pore volume in sandstones than there is in basalt, but the pores are a lot smaller. So there's some trade-offs there. Okay. Speaking of how easily you can inject and how small or large the pores are, so injection is obviously a dynamic process. You have to get the gas to flow through the rock. And so we have to think about a property called permeability. So in hydrology and in petroleum engineering, we use what's called Darcy's law to understand low Reynolds number flow through porous medium. And for those of you who are more familiar with kind of circuits and electronics, it's analogous to Ohm's law, where Q would be the current, and then K would be the inverse of the resistance. But anyway, for fluid flow, we have the flow velocity vector, and then we've got the pressure gradient that's applied to it over here. And this is the viscosity, and K is the permeability. And this describes how easily the fluid moves through the rock under an applied pressure gradient. It's kind of a funny unit. It has units either of meters squared, or sometimes we use a unit called the Darcy, which is named after the guy who came up with this law. He was a French civil engineer. And 1 Darcy is approximately 10 to the minus 12 meters squared. So there's a little bit of a funny conversion factor there. Okay, so we want rocks for CO2 injection to have as high a permeability as we can. And so we have to think about what are the controls on the permeability of the rocks. So a first order control is actually just how much void space you have. If you have no void space, obviously you're not going to be able to flow any fluid through that. And generally, the higher your porosity, the higher your permeability is going to be. But that's not always necessarily the case. Okay, it depends on the type of rock that you have. So here's a helpful diagram over here that shows you what some of the permeability to porosity relationships are, depending on what type of rock you're looking at. Sandstones are kind of in the middle in terms of their porosity to permeability relationship. But if you're looking at something like a chalk, which has relatively small grains and small pores, at a given porosity, you'll have a lower permeability. Whereas if you're flowing through fractures generally don't take up a very large fraction of the volume of the rock because they're very narrow and they tend to be spaced, fairly widely. And so your porosity will not be very large, but the permeability of a fracture is very high because you can flow things through it very easily. And so you have to think very carefully about what your the type of rock is that you're looking at. And you can't just assume that because you have a higher porosity, you have a higher permeability. It's a little more complicated than that. I think that's about all I need to say on that. So for your injection target, you want to look for the right combination of porosity which gives you the storage volume, and then permeability, which gives you the ease of injection into your rock. Okay, so here's a little thought experiment. If I inject carbon dioxide into a rock that has very low permeability, and let's say that I want to maximize the injection rate. So what I'll do, so if I go back to Darcy's law here, to get the injection rate to be higher, basically you have to increase the pressure that you're injecting in, okay? Now, what happens if you increase the pressure too far? What are you going to do? Yes, you will fracture the rock. And when when you've drilled a well in an organic shale and you do want to do a frac job, that's how you do it. You pump high pressure fluid down there. But when you're injecting CO2 into a saline aquifer, creating a fracture is actually a bad thing because then you'll have a preferential flow path and the CO2 won't fill the total pore volume. It'll just follow that fracture and you'll kind of lose your ability to store carbon dioxide in that aquifer. So you have to be very careful about how you manage the pressures during injection. Yeah, question. Can you use diverters? Yeah, I mean, that makes it expensive. It's probably easier not to create a fracture in the first place, but yeah, there's all kinds of technologies for, taking care of what happens when you do create a fracture. So for those of you who don't know, a diverter is a chemical that you can pump down hole to seal up a fracture or a particular zone in the well that you don't want fluid going into or coming out. Do you have a question here?
Yeah. What does it mean to have the depth have a gradient?
For the depth to have a gradient. So it's oh, I see what you mean here. Yeah, what is the grad of Z? So that comes from, that is looking at the gravitational field. Okay. And so Z obviously is a directional vector. So it increases at 1 meter per meter. So actually, when you work out the gradient of depth, it just is equal to 1. And so that goes away. So this is just a fancy way of writing this in vector notation. But yeah, in practice, this is typically written as delta, grad of pressure minus rho G. And you can even just put the gradient operator out in front of the whole term, the whole thing in parentheses here. So I've really just distributed the gradient operator. Okay, any other questions? Cool. Okay, I'm going to start off with, we're going to start on a little bit of the capillarity issue, and then we'll probably end it for the day. So there's something interesting that you have to think about when you're injecting CO2 into the subsurface. Carbon dioxide is a separate fluid phase from whatever's already there, okay? And that's going to be true regardless of whether you're injecting into a saline aquifer or into a depleted oil or gas reservoir. And so you end up having what we call multi-phase flow in the reservoir. And you have to think about the dynamics of that process and also how the CO2 interacts with the other fluids that are down there. And a lot of this goes to understanding what the seal capacity is, because the seal is going to hold your carbon dioxide in place by capillary forces. And so we have to understand what those capillary forces are and how they arise to be able to do an assessment of the seal capacity and ultimately the storage capacity of our sequestration target. Okay, so to start out, we'll maybe talk about something that is maybe not as obvious how it connects to carbon dioxide storage. And if you're in my petrophysics class or already took my petrophysics class, you kind of already know where we're going with this, but it's a useful review. Okay, so let's imagine you've got an array of glass capillary tubes of various sizes. When you insert them into a tray of water, the water will climb up the inside of the tube to a certain equilibrium height. Okay, we call that capillary rise. And we know that that equilibrium height is going to be inversely proportional to the diameter of the tube. So the smaller your tube, the higher the capillary rise is going to be. So the question is why? And there's really two reasons here. One of them is what we call interfacial tension, and the other one is what we call wettability. So interfacial tension, which is sometimes referred to as surface tension, which is how it's labeled over here, this happens at an interface between two fluids, because if you think at the molecular scale within those fluids, all all the intermolecular forces are balanced when you're in the bulk fluid. So the molecules are at some equilibrium distance from each other, and everything's happy. At the interface, these molecules right here don't have any neighbors up here that are exerting forces on them. And so to maintain equilibrium and keep those molecules from just spontaneously jumping into the other fluid phase, there has to be a net force, a tension that's acting in the plane of that interface. And we call that the interfacial tension. And the way that you can define this is thermodynamically, if we're at constant pressure, volume, temperature, and entropy, so everything is remaining constant, any change in the internal energy of the system can only be brought about by doing work on the system. There's no heat transfer, okay? And so if we're doing interfacial work, the only work you can do is changing the area of the interface. And the what we write is that the work that's done is proportional to the change in the area of the interface. And that constant of proportionality is called the interfacial tension. And what that means is that if we increase the area of that interface by some amount dA, the change in the internal energy of the system is going to be given by this equation here, where sigma is the interfacial tension. So that's how we define that. Now, an interesting consequence of this is if we want to minimize the energy of the system, that means that we need to minimize the area of the interface. And so that interface, if it's at equilibrium, it will always form part of the surface of a sphere because the sphere is the shape that has the lowest surface area to volume ratio of any shape. So if we go back here, this meniscus here is always going to be part of a sphere. It's not going to be exactly a hemisphere. And that has to do with this wettability property that we'll get to in a bit. But you form a little bit of a sphere. Okay. So I think we'll leave it at that. We'll come back to defining the pressure differential across the interface here on Monday. But I hope you all enjoy the weather this weekend, and I'll see you back here on Monday.